So what we're going to do here is just establish a couple additional concepts related to infinite limits, and then we'll talk about continuity. In the past, when we've evaluated a limit and said that that limit is approaching infinity, that's really not an appropriate way to evaluate a limit. If the value of a limit is infinity, we're saying that it's approaching some number, but infinity is not a number that it's approaching, so the most appropriate way to evaluate something like that would be to say that the limit does not exist. But there are times where we'll need to establish that although the limit doesn't exist, it is approaching positive or negative infinity for the purposes of establishing where an asymptote would be. So in example B here, it says to show that there is a vertical asymptote when x equals 2. The best way for us to do this is to investigate what it is that this function is approaching as x approaches 2. So I'd like to know what the limit of f of x would be as x approaches 2. And in order to know the value of this limit, we're either going to need to use a table or a graph. Now this is a function we should be pretty familiar with, so we'll sketch a little graph. This is a rational function with a horizontal shift 2 units to the right, so that would be our vertical asymptote. Looks something like this. And this right here would be x equals 2. So we could say then that the limit as x approaches 2 from the left of f of x would be negative infinity. And really, we would say that the limit does not exist because these values are getting more and more and more negative. They're not approaching a value. But what we're trying to establish here is there an asymptote? And in order to show that, we just have to show that either the limit on both sides is negative infinity, or it's positive infinity, or one is negative infinity and the other is positive infinity. And we could then say that the limit as x approaches 2 from the right of f of x, based on this graph, would be positive infinity, because as I approach x equals 2 from the right, it's approaching positive infinity. Now all of this is just kind of us thinking out loud so that we could say that the limit as x approaches 2 of f of x does not exist. But either of these two things is evidence enough to say that there is a vertical asymptote at 2. And we can't just say dne there because we're trying to make the point that these values are increasing rapidly or decreasing rapidly, although they're not approaching one specific value. So that brings us to the idea of a horizontal asymptote, which is what if the limit as x approaches infinity or negative infinity is some value? And we talked a little bit about this in class. Example 2 is going to give us the opportunity to explore that a little bit. So as x is approaching infinity, what I'd like to do is explore what the value of this whole thing is approaching. So we said that when x is approaching infinity, we can imagine that all of these terms, or any term at least that has an x value, has numbers being plugged into it that are getting increasingly larger. And so something like 1, well, that's not going to be affected by that at all. But this x squared is going to be affected by that, and the x squared in the numerator is going to be affected by that. So really this is just like evaluating the limit as x approaches infinity of 3x squared over x squared. And in this case, you could imagine that both the numerator and denominator have an x squared that are growing at the same rate. So they're not really going to be influencing each other. So the value of this limit is 3. What that means is that there must be a horizontal asymptote at 3 for this graph. In the past, the only way for us to find horizontal asymptotes was to find the inverse of the original function and then figure out where there would be a vertical asymptote of that function. But now with rational functions, we can use limits to find those horizontal asymptotes instead. So let's just apply that here to example 3. We're looking for the limit of this function, 5 minus 2 over x squared, as x approaches infinity. So what's going to be happening to the terms in this expression? Well, this 5 is not doing anything. I'm just plugging in values into 5, so that's just going to stay a 5. But this expression here has increasingly larger values in the denominator. So what's going to be happening there is the denominator is going to be growing, the numerator is not doing anything different, and so the value of this whole thing is going to be 0. So basically this is just going to be 5 minus 0. So that means that the limit of this function as x approaches infinity is 5. And then what that means is that this function has a horizontal asymptote at y equals 5. So if I were to sketch it out, I know that at 5, my function would be approaching that value as x approaches infinity. So it'll look something like that on this end. And if we take a look at example 4, I would say that the limit that I'm being asked to evaluate is going to give me the same value as if I calculate the limit as x approaches infinity of, say, 2x over x, because these terms are not significant. And that's just going to give me 2. So there must be a horizontal asymptote at y equals 2, which is a much more efficient way of doing things than what we used to do in the past. So I'll just remind you that in the past, if you had a function 2x minus 1 over x plus 1, we knew that there was a vertical asymptote at x equals negative 1, but what we didn't know is where the horizontal asymptotes were. So what we had to do is we had to say, okay, well, let's come up with the inverse function. And then let's find the inverse. We had to solve for y. And then we'd look at the vertical asymptote for that new function. That must be the horizontal asymptote for the old function. So that's how we used to do it. Now that we have limits, it's more efficient. So what I want to make sure that we have the opportunity to do here is to really bring the idea of continuity around full circle. We've said in the past that a function is continuous if you can just draw it without lifting up your pencil. It's not a very rigorous definition of continuity. So in introducing limits, we first came across the idea that, well, if the limit is equal to the value of the function at that point, then the function must be continuous. So now this is like the full rigorous definition for continuity of a function. We're going to make sure that we have this in our notes. There are 3 types of discontinuities that can exist, or 3 ways that a function cannot be continuous at any given point. And so these are those 3 ways. And I want to go through why they're called what they're called, because we're going to see that some of these are easier to deal with than others, especially algebraically. So first we have a removable discontinuity. It's called removable because when you have a function that has just a hole at some particular value, likely what that means is we're going to be able to factor out the value causing that hole and cancel it if we're evaluating this algebraically. So if we've got some value here, let's pretend that this is like x equals 2. Well, the equation for this function, because it's a hole and not an asymptote, what that means is that it's likely that as I evaluate this function, I'm going to find that there's a factor of x minus 2 in the numerator and in the denominator. And there's probably some other stuff too. But if I factor properly, I should find that I can remove that discontinuity, and then I could continue evaluating this limit using whatever pieces are left over. This is something that we've done in the past. When we encounter non-removable discontinuities, there is not going to be anything we can do about this algebraically. I'm not going to be able to just factor out an asymptote. An asymptote is there because that's in the denominator, and it's never going to be canceled or removed from that denominator. That's just stuck there. So this would be a situation where you might have an x minus 2 times something in the denominator, and in the numerator, there is no x minus 2 factor. You just have something else. There's no way for you to cancel that x minus 2, so it's a non-removable discontinuity, and it results in a vertical asymptote. For the non-removable discontinuity with a jump, well, this would have to be a piecewise function. So you're going to have a function that's explaining what's happening to the left of some value here, some value, whatever that x value is, and then a function that's explaining what's going on to the right of that value, and then you're going to have to explain what's happening at that value as well. So you could have a non-removable discontinuity or a jump discontinuity with a piecewise function, and you may have a non-removable discontinuity with a vertical asymptote in a rational function that you can't factor and cancel the piece of the denominator causing the asymptote. So a function is continuous at C if there is no interruption in the graph of f, i.e. no holes, jumps, or asymptotes. So 3 criteria need to be met. First, f of some value needs to be defined. So if we're checking to see, is it continuous at x equals 4? Well, let's check 3 things. First, does f of 4 exist? If it does, then we can check that box. 2, does the limit as x approaches 4 of this function exist? If it does, that's great news. And then finally, we just need to make sure that these two values are the same. This is what we've said in the past. We established this very early on in the unit. If the limit as x approaches this value is the same as the value of the function, then it's continuous at 4. So these are the 3 criteria that need to be met for any possible x value if we're checking to see if a function is continuous at that point. So is f of x continuous for this function down here at x equals 3? Well, first, is there a value that satisfies the equation f of 3? Can I do this, in other words? Well, it looks like I can because there is a place where this function is defined at 3. So I'm going to plug in 3 here. All right, so I can check that box because f of 3 is 4. 2, what is the limit as x approaches 3 of my function? Does it exist or doesn't it? Well, that's kind of a two-part question because I then need to make sure that my left-hand limit agrees with my right-hand limit. So as I approach 3 from the right, that would be four. And as I approach it from the left, that would be 4. So because my left-hand limit agrees with my right-hand limit, I would say that the limit as x approaches 3 is 4. Looking good so far. Now I just have to prove that this function is continuous by establishing that f of 3 equals the limit as x approaches 3 of this function, because they are both 4. So this is the full process for determining is a function continuous at a certain point. Checklist of 3 items that need to be investigated. So I'll be sending you guys the last couple pages of this notes sheet for you to complete on your own. That'll be your homework for tomorrow. And then tomorrow we will discuss continuity and sort of wrap up the notes on that concept. So we'll finish up this unit tomorrow. We'll do some review on Monday, and then we will do our unit test for the limits and continuity unit on Tuesday of next week.